Hi folks, welcome back. So we have come full circle. A few months ago we started with some kind of faux op-amp circuits using some CMOS chips. Then we looked at the two golden rules for analysing very simple op-amp circuits. Then we looked through some simple transistor circuits. Then we looked at some not so simple transistor circuits. And now we've come all the way back to looking at op-amps again. So first let's talk about what an op-amp is. So I'm sure many of you know that op-amp stands for operational amplifiers. Op-amps are circuits that were originally designed to execute kind of simple mathematical operations, but they have ended up being used in basically every circuit application you can think of because they are just so useful. But what is it that's going on inside an op-amp that makes it so useful and so versatile? Okay, so I'm going to be quite broad here and speak very generally because there are thousands of op-amps and they're all slightly different internally, but generally speaking they all follow the same kind of formula. So this is a simplified version of what you'll find in most op-amps. You'll start with some sort of differential amplifier, and then the differential amplifier's output will be passed into some sort of gain stage. This is just a common emitter amplifier, and then the output of the common emitter amplifier, or our gain stage as I'm calling it, will be passed out into a kind of output buffer stage. You won't often see BJTs at the input. You'll usually see either Darlington pair of BJTs, which is basically two BJTs one after the other, or you'll see a different type of transistor called a JFET, which for the purposes of this video we can think of a JFET as working just the same as a BJT, only it's got a very high input impedance. There's a little bit more to it than that, but we're just going to gloss over that for now. Okay, so what we're going to do now, I'm going to look through a couple of op-amp data sheets and just show you how what I've shown you on the board relates to real op-amps. Here we've got the TL07 series data sheets, very common kind of low cost op-amps. Let's go find the schematic in here. Okay, so here's the schematic for a TL071. TL072 is just two of these, TL074 is four of these. So I know this looks a lot more complicated than what I showed you on the board, which is why I've been explaining what I've shown you on the board is just a simplified version, is more of a skeleton circuit of this than anything else. So here we've got our differential amplifier. So these are the two input transistors. Remember earlier I told you that you'll often see JFETs instead of BJTs. These are what JFETs look like if you don't know. Here's our little current source, and we've got a load of active stuff up here. I don't want you to worry about what that's doing. So then that's passed out to here. This is our gain stage, right? So this is the common emitter amplifier. Here's our emitter resistor, and we've got all this stuff in the collector. These two transistors are acting like two diodes connected in series, which is what I showed them as in my circuit. If we look here, they keep these two transistors 2 VB drops apart. So if we start at this transistor, we've got 1 VB drop, 2 VB drops, and then the other transistor. So the circuit is set up so that when the output is at 0, so this point here is at 0, and this differential amplifier is outputting 0 as well, so we're at 0 here. So we're at 0 here, that this transistor is 1 VB drop above 0, and this transistor is 1 VB drop below 0, and what that means is that as soon as you go either positive or negative, this transistor will turn on or this transistor will turn on. Otherwise you're going to lose output voltage turning on either this transistor or this transistor, and that gives you a thing called crossover distortion. Distortion is bad, and so that's why we have these two diode connected transistors. So let's just recap here. We've got a differential amplifier here. Don't be thrown by the fact that it's upside down. So I've been drawing it with the differential amplifier and with the current source on the bottom and the kind of collector stuff on the top. This is just upside down. Don't get thrown off by that. Then that's passed off into this gain stage. Again, this is upside down compared to my drawing. Here's the common emitter amplifier. Here's those two diodes, and this is a current source here. And then we've got this output push-pull buffer thing. Okay, so let's go on and have a look at another op-amp. Okay, so this is the LF411, a very similar type of op-amp, a bit of a fancier op-amp. So let's have a look at the schematic on this one. Okay, so here's the detailed schematic. Much more complicated looking, much more complex op-amp, but at its core we will see that it's doing the same stuff. Again, we've got a differential amplifier here. Again, it's upside down from what we're used to looking at, but don't let that throw you. We've got two JFETs here. Here's that current source in the tail of the differential amplifier, current mirror and things like that going on. Again, don't worry about it. Let's just follow it through. So then that gets passed out here. We come down this way, and here we've got our gain stage. Here's that common emitter amplifier. Here's the two diode connected transistors. Here's the current source. and here's our push-pull output stage. Basically the same thing. So now let's have a look at another op-amp that's slightly different. Okay, so this is the LM393. So here's the schematic diagram for that, and what we can see is that it looks quite different, but again, it's more or less the same stuff that we've got going on here. So because we've got BJTs in here, remember how I said you either see JFETs or you see Darlington BJTs, and that's what we see here. So we've got two BJTs, one going into the other. Again, it's upside down, so we got PMP BJTs. But so we got here is the core of our differential amplifier. Here's the current source, and then the output is taken out, and here we've got common emitter amplifier. We've got a current source as the load, and now this one's slightly different because we've got what's called an open collector. So this time we don't have the push-pull output. This time we've got a high impedance output, and so this is a good example of a different type of op-amp, but you can see at its core we've still got a diff amp here, we've still got a gain stage, and we've got a slightly different output this time, but we'll get into why you might want an output like this in another video. Okay, so hopefully I've convinced you of what an op-amp is internally, and what I'm trying to get across in this bit is that while the op-amp schematics look very complicated and terrifying to look at all this stuff, look at all these bits, at its core, it's not anything that we can't understand with the things that we've done in these videos so far. It's essentially just a very high gain differential amplifier with a nice low impedance output buffer. All of this other stuff is just improving the circuit performance, making sure we've got lots of gain and it's very stable and all this other stuff. An operational amplifier just on its own has so much gain that it doesn't actually have that many applications. But with the use of feedback, we can control the gain and make op-amps into the versatile circuits that we know them as. So I've done a whole video on op-amps and their golden rules, which you can check out up here. But just as a quick recap, the most simple way we can analyze an op-amp, this is an op-amp, it has two inputs and one output. Two inputs, one output, okay? So if we apply 1 volt to the non-inverting input, that's this input here, then what's going to happen is, if we have negative feedback, which usually looks like feeding the output to the inverting terminal, the output will do what it can to make these two inputs the same. So in this case, if we applied 1 volt, we'd see 1 volt at the output, which would make these two inputs the same. This is how you make an op-amp buffer. We've looked at this in previous videos. The second golden rule is that no current can flow in or out of these inputs. In other words, they have a high impedance input, which is, as I said, why we usually see Darlington pair transistors here or JFETs. So Darlington pairs because you have two transistors in a row, they've got very high gain so they don't need much current, and JFETs work in a slightly different way, which mean that they don't need any input current. So that's why you usually see those. So I've just applied that same theory to our simplified internal circuitry of the op-amp. I've got feedback from the output to the inverting input. Let's have a look at how this works. So what we know from our differential amplifier is that if I apply a signal to this input, we'll see that signal out of phase at this collector. So we'll see minus whatever. Let's give this stage a gain of 50. Nice round number. So this collector will try to go to minus 50. Okay, let's forget about the power supply and all that for a second. And so this now gets passed into this gain stage, which also has a gain. Let's give this a gain of 20. Nice round number. Okay, and because this is a common emitter amplifier, we know that the collector here is going to be out of phase with the base. So minus 50 times 20, inverted here, so it's times minus 20 really, is going to give us 1000 at the output. So the output is going to try to go to 1000. Obviously the output is not going to be able to go to 1000 volts because let's say we've got a power supply of 10 volts and our negative power supply is minus 10 volts. So it's going to get limited at 10 volts, but let's just imagine these unlimited voltages for now because it paints a better picture of what's going on. So the output, which is fed back into this input, let's assume the output starts at 0 volts. So the output starts off at 0 volts and then the output wants to go towards 1000 volts. Well, it can't go from 0 to 1000 volts straight away. This is an analog circuit, so it has to go through every value between 0 and 1000 volts. So let's pick out some values on the way and see what happens. what's going to happen is this output is going to get to 0.9 volts, let's say. So at 0.9 volts, so if I draw this on a graph, we've got a graph here, and so this is our 10 volts power supply. That's going to be 1 volt. So this is what our non-inverting input is at. And so we've gone up, we're going towards 10 volts, and we've gone up to 0.9 volts. And now let's see what's happening at this input. Okay, so now what's happening? This is a differential amplifier. What's going to happen is it's going to amplify the difference between these two inputs. So before the difference between the two inputs was 1 volt. So we got to minus 50 volts. So now it's only 0.1 volts. So now this is trying to go to minus 5 volts. Now minus 5 times 20, this is going to go to 100 volts. So you can see it's still going to be limited by the 10 volts power supply, and this is why I left it in these unlimited values. But essentially what's happening here is the rate is going to slow down as we approach this 1 volt point. And so now let's have a look again at when we're at 0.99 volts. And so now there's a 0.01 difference between these two inputs. 0.01 times 50 is minus a half. So this is going to try and go to minus 0.5 volts. And then minus 0.5 volts times 20 is 10. So the rate of change is going to slow down still. So what's happened here is we're slowing right down as we approach this. And then eventually we will get approximately equal to 1 volts. I mean, technically you never get exactly to 1 volts, but for all intents and purposes, we'll get to 1 volt, and then there'll be no more difference between the two inputs. So there's nothing left for the differential amplifier to amplify. And so then the output has made these two inputs equal. So the output holds this at 1 volt. And if it tried to dip down even a fraction below 1 volt, that would cause a difference between the two inputs. That difference would be amplified, and then the output would compensate for that. So that's how the op-amp is actually holding itself at that voltage. And just to kind of highlight that, so now if I set the non-inverting input to 0 volts, let's see what happens. So now, if we're thinking about in terms of our differential amplifier, so now we've got an input on this input here. This is what we're taking the output from, isn't it? So we remember that the collector opposite to this transistor is in phase, and the collector on the same side is out of phase. So we'll see this input go up by 1 volt times the gain. And remember, this circuit had this section had a gain of 50, section had a gain of minus 20. So we'll see 1 volt times 50. This is why it was inverted when it was on this input, but now it's not inverted because we're on the other input. Confusingly, we're on the inverting terminal, so it gets inverted and then it gets inverted again. So we've got 1 volt times the gain. It's on the opposite collector, so it's in phase. So this collector tries to go up by 50 volts. Remember, we're just talking in relative what the circuits are trying to do, not what they're actually doing. Obviously, this is at some quiescent voltage. It's limited by the power supply. So we're just going to forget about that for a second and just think in terms of these imaginary voltages, for want of a better term. So then this 50 volts gets passed through this minus 20 volts, which means the output is going to try and go to minus 1000 volts. And so essentially the same thing's going to happen again in reverse. So we initially set this to 1 volt, and the output we saw went up and met 1 volt, and then we held it at 1 volt for some amount of time, and then we set the non-inverting input to 0 volts. So this is the part we've already gone through. So now the output is going to try and go all the way down to minus 10. But again, as it approaches this 0 volts, the difference between these two inputs becomes smaller and smaller, and so the rate of change of the output slows down. Okay, and then that will hover around 0, and that's all there is to it. Let's go and have a look at this happening on the oscilloscope. So we've got a very simple circuit here. It's literally just an op-amp. So what I'm doing is I'm showing you the blue signal on the oscilloscope is the output, the yellow signal on the oscilloscope is the non-inverting input. I've got the inverting input grounded at the moment. Okay, so if we look on the oscilloscope, what we can see is that the output has just gone right down to the negative supply. So there's obviously a tiny difference between those two inputs, and that's being amplified to send it to the negative rail. So what I'm going to do here is I'm going to turn the non-inverting input to 1 volt, and we're going to have a look at what happens at the output. Okay, so let's see what happens. So the yellow signal is the input and the blue signal is the output. Remember I've got the inverting terminal grounded, so as soon as the input, the non-inverting input, goes above ground, the output goes all the way up to the positive supply voltage, because we've got no feedback. As soon as we get some tiny difference between those two inputs, the huge amount of gain internally to the op amp gains that tiny difference all the way up to the positive supply voltage. Yeah? Okay, so now let's see the difference with a bit of feedback. Instead of grounding the inverting terminal, I'm going to feed the output back to the inverting terminal. So now we've got negative feedback. So straight away we're seeing a difference, and that is that the two inputs are already being held the same. So we can see the two inputs here sitting right one on top of the other. So now let's see what happens with the output. So the output has followed the input almost exactly. And so obviously it takes time for the input to be set, and as that happens, the output changes and the differential amplifier keeps those two things the same. And let's turn it off so you can see the same thing in the opposite direction. So as I turn the input down to ground, you'll see the output follow the input. Much quicker to turn off. So the input switches off, that's the yellow signal, and then the output follows it very soon afterwards. We do have some steady state error. We'll talk about those differences between the two inputs in a future video when we talk about how real op amps don't behave like our perfect op amps in our models do. Okay, so there's no magic or sentience going on inside this op amp. I know op amps seem very mysterious, and so now it's straightforward to see why we get gain out of this, because the exact same things happen, only we just put a voltage divider here. Then if we say these two are both 1k, the value isn't important, but these are both the same. So now, to make this point, if we apply this 1 volt again, this output is going to go towards the positive supply, and it's just now able to keep going for further before these two inputs become the same. Because now, if the output reaches 2 volts, now there's 2 volts here, but because of this voltage divider, has divided down from 2 volts, now this input is 1 volt, and this is obviously 0 because it's ground. And so now these two inputs are the same, so the op amp just stops amplifying because there's no difference left for it to amplify. Okay, so the important thing in this video is that we've looked at this and we've convinced ourselves that we can approximate this op amp as a high gain differential amplifier with a low impedance output buffer. Now that I've hopefully convinced you that that's true, we can do something that's very important. We can look at this, even just this simplified schematic and definitely the detailed schematic, and go, there's a lot more to it than that. But you see, what's important is that we don't care. What we can do now is we can forget about this. We can forget about those detailed schematics, and we can throw it all in the bin, and we can say, I don't care about how much current is shared from one transistor to another. I don't care about the VBE drops in between the two output transistors. I trust that the IC designers have done their job properly and that all of that is taken care of for me, and I can only I can worry about the two inputs and the one output. And I can think to myself that this is now just a block that has two inputs, some sort of input impedance, some sort of output impedance, and a whole load of gain. And we can think about the op amp only in terms of these things, forget about what's going on internally. And so we can say that we know that we've got some voltage across here, and that voltage is multiplied by this gain and then goes through this output impedance, and that's all we need to worry about. And if we use our golden rules by applying some negative feedback, and then we don't even have to worry about the gain, because we're now constraining the gain. We're now setting the gain with this external circuitry, and this is super powerful because we now have a much simpler way of thinking about what is actually quite a complicated little circuit going on inside there. So next video we're going to leave behind the transistor model of the op amp and look at it as just an ordinary op amp, and we're going to see how this op amp is able to make our circuit design process easier. Even when we're still using transistors, we can hide some of the things about transistors that are annoying and difficult with op amps, and we'll work these improved circuits into the VCA that we've been working on for a few videos now. So please come back for that. I hope you've enjoyed this video. Leave a like and all that kind of stuff. Please come back next time for that, and I'll see you then. Bye.